Let's take a look at another radical halogenation. And this time we're going to be talking about allylic bromination, right? So allylic bromination, you're thinking allylic position with a bromine on it, right? So this is the allylic position, right? It's the carbon next to the double bond. And so if you're thinking about this, you're like, okay, I'm going to take my alkene here. I'm going to add my Br2 with my light, and then I'm going to undergo some kind of radical halogenation to add a bromine to this. And so you go ahead in the lab, you do this experiment, and what you end up with is this compound right here. So that's obviously not what you wanted, and so we'll cover this mechanism later. But the end point is that when we're talking about alkenes, we can no longer just use Br2. It will not undergo this radical halogenation. And so we need a different reagent. And the issue is this Br2. When you have Br2, it's going to add across the double bond. Again, we're going to learn that later. And so we need something that's not going to do that. And the answer to this is NBS. It stands for N-bromosuccinimide. It looks like this compound right here. Where we have this nitrogen Br bond that's very weak. And we can shoot some UV light at it, and it'll easily form this radical. If you think about why this bond is weak, first of all, it's an NBr bond, but also this radical is resonance stabilized. And of course, we'll get a bromine radical, right? So we avoid forming Br2 in large concentrations. We do actually form some Br2, which is actually important to the mechanism, but it's in very small concentrations. And so this time when we take our alkene, same as before, but now instead we're using NBS with some UV light. We get bromination at the allylic position. And if you think about what's going on here, what's the rate determining step is the hydrogen abstraction. This is the rate determining step, so this is kind of the most important step. And so it's going to happen at the most stable position, which in this case is the allylic position, right? So we've got our cyclohexene there, and then we've got our bromine radical. It's going to abstract this hydrogen and then leave a radical right there. This radical will then actually interact with a molecule of Br2, not a Br radical, to form our final product, and then yet another bromine radical that can then continue and propagate the cycle. And so you can see the mechanism here, and we get our allylic bromination, whereas if you just use straight up Br2, even if you add some UV light, you're going to get this 2-bromine substitution. And so let's take a look at how you're going to do these mechanisms and solve these problems. So we have this compound right here. We're going to add some NBS to it with some UV light, and I want to know what the product you're going to get is. And so this is kind of a two-step problem. The first step is to form the radical. At the most stable position. So the first thing we do is we identify that we have a double bond, which means that we have 2 allylic positions, right? Both of these are allylic positions. This allylic position is secondary. This allylic position is tertiary. So we're going to form with the tertiary allylic position. Right? It's more stable, so that's where it's going to go. This is the rate determining step. And so you have a radical right there. And then this radical can go ahead and interact with some Br2. To form your product right here. And cool, you think you're good to go. But wait a second, you do the experiment in real life and you see that this is not the only product that you get. You also get some of this. So how the heck did we get to this? Well, think about this structure right here. It's got this allylic radical, which means it has resonance. It has a resonance. And so you can draw a resonance structure for this. You can move this radical down, move one of the electrons from the double bond here, and move the other electron here. And so then what you'll end up here is the radical down at this lower position. Which can then interact with some Br2 to form your other compound. And so you can see we have two of these products. And so naturally what you may be thinking is, which one of these is the major product? And the answer is it depends. It depends on your conditions. This one on the left is the kinetic product. And that's because it comes from the more stable intermediate, right? This tertiary carbocation is more stable than the secondary carbocation. So it's got a more stable intermediate, so it happens faster. That's the kinetic product. However, this one on the right is the thermodynamic product, which means that it's more stable at the end, right? And we'll learn about this later. This is called Zaitsev's rule. We'll learn about this later, but basically the thermodynamic product is going to be the one with the more substituted alkene. So if you take a look at this alkene, it has 1, 2, 3 substitutions on it. A hydrogen does not count, whereas the alkene over here has only 1, 2 substitutions on it. So again, we'll dig into deeper later on, but for now you just want to identify all the products of these radical allylic brominations. Just some other key points here. If we have toluene here, our benzene with a methyl group, and we add some NBS and some UV light, we'll generate a radical at this methyl position, which is free to undergo resonance throughout the ring. However, the bromine substitution will only occur on this methyl group. The bromine will not substitute out in the aromatic system. And the reason it won't do that is because you then destroy the aromatic system, which is very energetically disfavored. We'll learn a little bit more about this when we get to aromatic systems, but for now you need to be able to identify the product of this reaction. Let's go ahead and take a look at another example. So we have this guy right here, add some NBS and some UV light. And we're going to go through our 2 steps. Our first step is to identify the most stable carbon. And so both of these carbons right here are allylic positions, so they're going to be the most stable. If you think about this molecule, it's symmetrical, so it doesn't matter which one you pick. And so we'll draw the product of the hydrogen abstraction, right? We took off that hydrogen, we left behind our radical. And then the second thing that we do in these reactions is we think about our resonance. So remember, this thing can resonate. To have our radical up here. And you want to go ahead, draw the arrows for yourself, make sure you understand this. And then either of these can interact with some Br2 to give our final products. So that one will give that one. And then this one over here will substitute this bromine onto this methyl position. Of course, this one right here, it has a stereocenter, but it's going to be racemic. So be careful. That's one trick some instructors use. They'll say draw all three products, and so they want you to draw one with a wedge, one with a dash. So just something to keep an eye out for. I won't really ask, but in case you meet an instructor that does. And this is going to be the kinetic product because it comes from the more stable carbocation, right, or carbon radical. This is a secondary. This one's a primary. And this one over here is going to be the thermodynamic product because it has the more substituted alkene, right? This alkene has 1, 2, 3 substitutions on it, whereas this one only has 1, 2. If you see this on some kind of standardized test or something like that, and they don't tell you about the conditions, right, whether to ask for the thermodynamic or the kinetic product, the one that they're asking for is the thermodynamic product. So just something to keep an eye out for.